बाकी स्टूडेंट्स को भी बोलो जल्दी ज्वाइन करेंगे।
तो चाहिए ना।
Am I audible?
Yes, sir.
Yes, sir, you know.
Oh. So this is the theory class for transport phenomena. Okay, the design class we will take on Friday. So So in last class we have studied the different basic properties which is used in the momentum transport. Now we started the momentum transport, and in the momentum transport we have studied the different basic properties. Like pressure, velocity, linear velocity, average velocity. Then we studied the volumetric flow rate, mass flow rate, all of these. Okay. Now we have also completed the no slip boundary condition. So I am just quickly revising the no slip boundary condition. What is no slip boundary condition? This is widely used in the momentum transport, no slip boundary condition. है ना? In every problem you have to use this assumption that no slip boundary condition is applicable. Okay. So according to this assumption, according to no slip boundary condition, whenever fluid comes to the contact with a solid body, suppose this is a solid surface and fluid is flowing above this solid body. Okay, so whenever the fluid comes into the contact with the solid body, the velocity of the fluid, the layer which is adjacent to the solid surface, the velocity of that layer is equivalent to the velocity of solid surface. If the solid surface, the velocity of due to the friction force. Okay, so if the velocity of the solid surface is zero, if velocity of solid surface is zero, then the velocity of this layer, and the layer which is near to the solid surface, adjacent layer, है ना? तो the velocity of that layer is also zero. Okay, so this is the first basic assumption used in the momentum transport. Okay, so you can say whenever a fluid comes in contact with any solid boundary, the adjacent layer of the fluid in contact with the solid surface has the same velocity as the solid surface. That's a layer of the fluid in contact with solid surface has the same velocity as a solid surface. Okay, so this is the assumption of the no slip boundary condition. Okay, the one thing which is remaining in the coordinate system. So we have studied the coordinate system in the previous class. So there are three type of coordinate system used in the transport phenomena. What are the coordinate system? Cartesian coordinate system, cylindrical coordinate system, and the spherical coordinate system, that we have already studied. So there are three type of coordinate systems. Cartesian coordinate system, second cylindrical coordinate system, and third is the spherical coordinate system. Okay, these are the three types of coordinate system used in transport phenomena. Now, the question arises that why we have to use all different types of coordinate system. Okay, so it depends upon the geometry of the channel or geometry of the system. Okay, so there are different types of system present in the which we will study in the transport phenomena. So the geometry of the transport system, है ना, that will decide from where we are by analyzing the geometry of the transport system, we have to decide which coordinate system we need to use. Okay, so I'm giving you the example. Suppose you have to solve the problem you have to solve the problem to calculate the flow inside the pipeline. Okay, you want to determine the flow inside a pipeline. So this is a pipe. Now, which coordinate system we will use in this case? Anyone? Which coordinate system we have to use in this case? Flow inside the pipeline.
Cartesian.
Why?
Sir, it's totally depend upon the flow of the liquid ना, so हम distribute कर देंगे x और y axis पे.
Okay, so देखो, this is
The
the
cylindrical.
cylindrical. Okay, so basically the fluid flowing inside a pipeline. Pipe has the cylindrical structure. Okay, so suppose you are assuming that flow is you want to solve the problem with the Cartesian coordinate. Actually you can use any coordinate system, na? But mathematically problem become more typical if you are choosing the wrong coordinate system. Okay, you can use any coordinate system, the answer will be same, the final solution will be the same. But if you choose the wrong coordinate system, your mathematically problem becomes the more complex. Okay, so suppose you are taking the Cartesian coordinate system. Okay, so I am drawing the Cartesian coordinate system outside the diagram. Okay, this is the Cartesian coordinate system, x, y, z. Okay, now fluid is flowing in this direction inside the pipeline. You know, this is the pipe, fluid will flow in this direction. So here you have the velocity v, you know, linear velocity v, where the velocity will depend. Now the velocity will depend in which direction. Okay, suppose this is a pipeline. This is the cross sectional of the pipeline. So at the midpoint, the velocity will be more at the middle of the pipeline, because here the fluid there is a very less friction, because in all directions solid boundary is very far. Okay, maximum, you have the maximum distance from the solid boundary. So here at the middle point you have the very less resistance. So the velocity at this point, at the middle point, will be maximum. Okay, and velocity at the boundary, at the solid boundary, will be zero, because pipe is in the stationary condition. Okay, so velocity at the fluid velocity at the boundary will be zero. Okay, so now if you are taking the if you are taking the Cartesian coordinate system, so this direction will be one direction. The fluid is flowing in the y direction, है ना? So because fluid is velocity is a vector quantity, so it has a direction. The fluid is flowing in the y direction, which may depend upon x as well as z direction, है ना? So it may depend upon x direction also and z direction also. Okay, so you have to write, if you are using the Cartesian coordinate system, you have the Vy, which may depend upon x as well as z. Okay, so once you develop, when you develop the equation, you will get the differential equation like Vy divided by Vx plus dvy divided by dz, because it will depend upon x as well as z direction. Okay, so you will get the partial differential equations. And when you solve the momentum transport problem, the equations will be even more difficult. And the equation will be even the more difficult. You may have the second order partial differential equation. So when you have the second order partial differential equation, you cannot solve easily. That required very high computational power. Very difficult. The mathematically problem becomes the very difficult. Now, if the same problem, in the same problem, you assume the cylindrical. If you assume the cylindrical coordinate system, okay. Suppose you have assumed the cylindrical coordinate system, okay, and you put the coordinate system accordingly. Okay, so because fluid is flowing in this direction, you have the symmetry in from the center. So we took the origin at this point. This is O. O is the origin. This direction is Z. This direction is R, and this angle is theta. Okay, so we have taken the, this is the Z axis, this is R axis, this is theta axis. Okay, now at all is this direction, these all direction are now represented by the R axis only. Okay, now you have the velocity V Z, because velocity is also vector quantity, so velocity is a Vz, and it will depend upon only the R direction. Okay, so you have the ordinary differential equation. You will get the ordinary differential equation, which is in the form of dvz by dr. Now, this is the ordinary differential equation. Even if it is a second order equation, second order ordinary differential equation can be solved analytically. Okay, so you can solve the second order differential equation. Even the first order ordinary differential equation or second order ordinary differential equation can be easily solved. Okay, so based on the geometry, you have to consider the coordinate system. The simple way to understand it, that if the geometry is cylindrical, take the cylindrical coordinate system. If the geometry is rectangular, take the rectangular coordinate system. Okay, the second problem is, suppose there is a two parallel plates, and fluid is flowing in between these parallel plates. Okay, then you have to take the Cartesian coordinate system. Okay, then you have to take Cartesian coordinate system. You can take x, y, and z. Okay, you can easily take the Cartesian coordinate system. Example of the heat transfer. Suppose you have the fins. You know the fins? Fins are used to eliminate the heat from the heated system. Okay, suppose you have an engine. You can see the fin in the motorcycle engine. In the motorcycle engine, you will find that there is a extended surface. So what is the work of this extended surface? They will remove the heat from the, they will disperse or the heat from the engine to the environment. Okay, so these are the metal surface. So metal surface will provide the extended area which can remove the heat from the engine to the environment. Okay, so you may have the cylindrical fins also, or you may have the rectangular fins also. If you are solving the problem for the rectangular fins, Then you have to take the Cartesian coordinate system. If you are solving the problem for the cylindrical fins, then you have to take the cylindrical coordinate system. Okay. Now the next example is the bearings. Suppose you have a spherical bearing which is present in a moving part. Okay, so this is the spherical bearing which is present in the moving part. Okay, and bearing is rotating in this axis horizontally. Okay, there is a lubricant present in between the bearing, and you have to determine how much friction is created by this lubricant and how much force is exerted on this external surface due to this lubricant. Okay, so this bearing is moving in this direction, and you have the lubricant in between the bearing, and you have to calculate how much force is faced by this outer surface. This is the simple example of the movement and the working of the bearing. Now in this case, you have to consider the spherical coordinate system. Okay, this axis, the horizontal axis will be phi, the vertical movement axis will be theta, and this axis will be, this is the origin O, and this is the radical direction R. Okay, so you have to take the spherical coordinate system because your movement is in the phi direction. If you take the cylindrical coordinate system or the Cartesian coordinate system, then the problem will become very difficult to even to formulate the problem. To determine that, to formulate the equation will be very difficult in the Cartesian coordinate system, in the cylindrical coordinate system. So based on the geometry, here your shape is cylindrical shape. So you have to make a cylindrical. You have to design. You have to consider this. This is the spherical shape. So you have to consider the spherical coordinate system. Okay. The next example is, suppose there is a spherical reactor. Reaction is occurring in a spherical shell. This is a spherical reactor. Or more simple example, suppose there is a spherical fuel ball. So suppose this is a catalyst, spherical catalyst. There is a catalyst which has the spherical shape, and the reaction occurs at the surface of the catalyst. There is a film of air film around the catalyst. So there is a air film. So this is the film of air which is surrounded by the on the catalyst, and here concentration is Ca naught. At the surface, your concentration is CaF. So now you have to calculate rate of diffusion of the component A. A is the reactant. Rate of diffusion of reactant from the surface to the from the bulk to the catalyst surface. Okay, and suppose the reaction is A tends to B. This is a simple reaction, and then you have to calculate the diffusion of B from the catalyst surface to the bulk. Okay, that you have to calculate rate of the diffusion from of A from the bulk to the catalyst surface, then the rate of diffusion of B from the catalyst surface to the bulk, that you have to calculate. Because this catalyst, we have assumed this catalyst has a spherical structure. Now you have to consider the spherical coordinate system. Okay, so based on the geometry, you have to consider the coordinate system. Okay, as well as okay, as well as you have to also consider the you have to put the origin and the coordinates also very carefully. Okay, you can, even if you have taken the spherical coordinate system, you can start the origin, you can put the origin at this point also. Okay, this is R direction, this is theta direction, and this is phi direction, and this is theta direction. And you can put the coordinate system in like this also, or you can put at this point at the center of the sphere, at the center of the catalyst. Okay, so you have to remember, try to try to put the coordinate system in such a way that you will get the symmetry in the system. Okay, your system will be symmetrical. Okay, suppose you are solving the flow inside the pipeline. Okay, so you have to substitute the coordinate system at the center of the pipeline. Okay, then only you will get the symmetry in the system. Okay, if you take the at a corner, then your symmetry will be not there. Okay, so you have to put the coordinate system at the center of the pipeline. Okay, so that is very important when you solve the problem. Okay, when you solve the transport phenomena problems. Okay, so make sure that you should take the coordinate system very carefully. Okay, so we have completed the no slip boundary condition, how to take the coordinate system. Okay, now the next topic is Newton's law of viscosity. So you have studied the Newton's law of viscosity before? Anyone?
Yes, sir.
So what is the Newton's law of viscosity? This is the basic empirical law which derive the which define the types of fluid. Okay, so basically this is the empirical law. What is the empirical equation or empirical model? There are two types of model. First is the theoretical model. Second is the empirical model. Okay, so empirical models means the mathematical models which is derived from the experiment. Okay, so there is no basic theory behind this Newton's law of viscosity. The Newton's law of viscosity basically derived from the experimental data. And so Newtons have done some experiments. They observed some pattern in the results, and based on that pattern, he derived a equation. That equation is called the Newton's law of viscosity. Okay, so I am for explaining the Newton's law of viscosity. I am giving you a hypothetical experiment. Okay, so from this hypothetical experiment, you will understand what is the Newton's law of viscosity. Suppose you have the two parallel plates. So these are the two parallel plates. Okay, the distance between the plate is h, capital H. Okay, the length of the plates are significant. They are very large. This is very long plates. Okay, and distance between the both plates is h. Okay, so length is L, which is very long, significantly large plates. Now there is a fluid which is present between the both plates. Okay, so you have a fluid which is present between the both plates. Okay, the cross sectional area of the plate is A, capital A. That is the cross sectional area of the plate. Okay, now at a time t equal to 0, both plates are at stationary condition. At time t equal to 0, both plates are at stationary condition. Okay, now what you have to do, you have to you have to remain you have to put the force F on the bottom plate. You have to apply the force F on the bottom plate, and when you apply the force F, you will see that this bottom plate starts to move, and the kept above upper plate stationary condition. You have to keep the upper plate at the stationary condition. This plate remain stationary. Okay, v equal to 0, and the put force F or apply force F on the bottom plate. Okay, now after some time you will observe that bottom plate start to move with the velocity v. Okay, so when you apply the force, when you apply the force when you apply the force F on the bottom plate, it will move. After some time it will move with a constant velocity v. Okay, now you have to repeat this experiment with different forces, and you will get the different velocity. Suppose you have taken the value of force F1, F2, F3, F4, F5, F6. These are the different values of the velocity forces, and respectively you will get the velocity v1, v2, v3, v4, v5 and v6. Now what you have to do, you have to divide the force from the cross sectional area of the plate. You have to divide the force from the cross sectional area of the plate. So F divided by A. Okay, so you will get the F1 divided by A, F2 divided by A, F3 divided by A, F4 divided by A, F5 divided by A, and F6 divided by A. These are the value of the stresses. You have to divide the force with the area and divide velocity with the distance between the two plates. Okay, so you will get v1 divided by h, v2 divided by h, v3 divided by h, v4 divided by h, v5 divided by h, and v6 divided by h. Now if you plot both quantities, this is the experimental method, you are doing the experiment. Okay, now if you plot the both quantities like v by h and f by a, you will get a straight line. Okay, and that straight line will cross through that straight line will pass through the origin O. Okay, so you will get a straight line which will pass through the origin O. So from this experiment you can say that F by A is proportional to V by H. Okay, so this experiment tells you that this is a hypothetical experiment, but you can do experiment. You can actually perform this experiment also. Okay, when you perform, you will find that for most of the fluid, and for most of the general fluids, if you take the different fluids, why you have the velocity v, different velocity, because the friction of the fluid. Here you have the plate which is in a stationary condition. In between you have a fluid. So due to the friction of this fluid, due to the resistance of this fluid, you have the different velocities. Okay. So when you plot, you will get F by A is proportional to V by H. Okay. And when you remove, or you can say at the zero velocity, at the zero force, the plate is in stationary condition. So you can write F minus 0 divided by A is proportional to V minus 0, because at the zero force you have the zero velocity by h. Or if you write this in the differential form, this F by A can be written as tau, shear stress. Okay, so tau xy is proportional to ddy by dx. Okay, tau xy is proportional to ddy by dx. When you remove this proportionality sign, you will get a constant minus mu ddy by dx, and this is the Newton's law of viscosity. Okay, so based on the experiment, this is an empirical model, this is an empirical law. So this law is not derived from the theory, basic theory. This law is derived based on the observation, based on the experimental observation. So Newton had performed this experiment, and he found that the forces per unit area and the velocity per unit length, per unit distance is proportional to each other for the different types of fluid. He performed the experiment for the water, for different types of oil, for different type of waxes, and he found that for all of these fluids, this law is true. So he derived this equation. That equation is Newton's law of viscosity, where mu is a proportionality constant, and that is called the viscosity. Here mu is a proportionality constant, and that is called the viscosity. Okay. So what is the viscosity? Viscosity is the resistance to flow. And basically what viscosity signifies the resistance to flow. Okay. So U is a property of fluid is a property of fluid. And for water you have the different value of viscosity, for oils you have the different value of viscosity, for air you have the different value of viscosity. So it is a property of fluid. Okay. And is measured the resistance offered by the fluid to flow. Okay, so this is the viscosity. Other quantities in the Newton's law of viscosity, tau xy. Tau xy is a shear stress. Okay, tau xy, it is a force per unit area. It is not a pressure, it is a shear stress. It is a friction. Basically, when you are talking the pressure is a compressible force. Pressure is a compressible force. But when you talk about the shear stress is like is like a friction, and a friction in the fluid. And when you talk the friction in the fluid, so that friction force is the shear stress. This is the force per unit area. So this is the friction force. Okay, the friction force per unit area, and it is a, in this case, the first indices, this is a second order tensor quantity. Pressure is a scalar quantity. Hydraulic pressure is a scalar quantity because in all direction you will feel the same pressure. Okay, at a given point, in all direction you will feel the second same pressure. There might be direction where the pressure is changing, but at a given point you in all direction. Yeah, तो ऐसा हो सकता है. It is possible that suppose fluid is flowing inside a pipeline. Okay, suppose fluid is flowing inside a pipeline. So at one point you have the pressure P1, at other point you have the pressure P2. That is possible that pressure is changing inside the pipeline. But at a given point, suppose this is a point A. So at this point, pressure in all direction will be same. And there is no preferred direction of the pressure at a given point. That's why pressure is a scalar quantity. It is possible that point A and in between point A and point B, there is a difference in the pressure. And here pressure is PA, at point B pressure is PB. And PA might be greater than PB, but at a given point pressure will be same. There is a no preferred direction of the pressure. Okay, so pressure is a compressible fluid force, and at all direction for hydraulic pressure it is same in the all direction. That's why pressure is a scalar quantity, although it is a force per unit area, but it is a scalar quantity. But however, the shear stress is also force per unit area. It is a tensor quantity, second order tensor quantity. Okay, now there are two indices x and y. So both they define the different things. Okay, so the indices, the first indices x. represent the direction of the surface where the force is applied. And second indices Y represent the direction of force. Direction of force. Okay, so when you write tau xy, so it represent basically the x represent the direction of surface and y represent the direction of force. Okay, so suppose you have a, this is a plane, this is a surface, and fluid is flowing. This is the Cartesian coordinate system. This direction is x, this direction is y, this direction is z. Now fluid is flowing in this direction. So what is the shear or the force is applying? You have applied the force in this direction. Okay. So what is the shear stress value? What is the shear non-zero shear stress value? Batao anyone? So what is the direction of surface? In this case, what is the direction of surface?
Y, sir.
Not y. Direction of surface is always the outer normal direction. है ना? So one thing you have to remember, any direction of any surface. है ना? How to define the direction of surface? है ना? Surface is a vector quantity. है ना? Surface cross-sectional area in the transport phenomena in the physics at all. है ना? In the physics, surface is a vector quantity. Surface has a direction. है ना? आप जो surface है वो किस direction पे है surface? सरफेस की डायरेक्शन कैसे डिफाइन होती है? हाउ टू डिफाइन द डायरेक्शन ऑफ सरफेस? दैट इज द आउटवर्ड्स नॉर्मल डायरेक्शन. ओके, सो दिस सरफेस हैज द आउटवर्ड नॉर्मल इन द जेड डायरेक्शन. तो डायरेक्शन ऑफ सरफेस इज जेड,
ZY.
है ना? है ना? एंड डायरेक्शन ऑफ फोर्स इज वाई. सो टाउ वैल्यू इज टाउ जेड वाई. ओके, if the direction of in this case direction of surface is y, suppose fluid is flowing in this direction, so direction of or the force is in this direction, then you have the direction of the force is x. So in this case you have tau y x. First indices represent the direction of the surface, second indices represent the direction of force. Okay, so that is the, in this way we have to define the shear stress. है ना? The units is newtons per meter square. SI unit of the shear stress is newton per meter square. Okay, force per unit area. Okay, now the third quantity is dvx, dvy by dx, dvy by dx. The third quantity is dvy by dx. So this is a shear rate. Basically, this defines the rate of change, change of the rate of change of the velocity in a given direction. Okay, so basically, when you have the friction force, whenever you have the friction force in the fluid flow, then the velocity will change. Okay, in a given direction. है ना? Suppose there is a friction force in this case, then the velocity will change from this. This is a pipeline, है ना? Fluid is flowing inside the pipeline. Okay, so fluid is flowing inside the pipeline, so you have a friction force in this direction. Okay, so when you have the friction force, then the velocity of the fluid will change, है ना? From the this direction. Okay, so this is the shear rate. Shear rate represents the changing of the direction of velocity and a flow. Okay, so at the middle point you have the highest velocity, at the boundaries of the tube you have the zero velocity. Okay, so in this way you have the velocity profile. So velocity will be maximum at the center of the pipeline, and velocity you have the least velocity or the zero velocity at the boundary of the pipeline. Okay, so the velocity is changing in this direction, that is the dx. Dx is the direction where velocity is changing. So suppose you have a two parallel plates. This is the y direction, fluid is flowing in the y direction, and this is the x direction. So when the bottom plate is moving, so the velocity of the fluid is changing. Here you have the velocity, the adjacent layer have the velocity vy. This is the, here you have the velocity 0 because this plate is in the stationary condition, so the velocity at this plate is 0. So you have a velocity profile. So when you move toward in the x direction, you have the velocity will change. Okay, so that's why you have the dy by dx. So dy by dx is the shear rate, which signifies the rate of change of, which signifies the velocity gradient. Okay, this signifies the velocity gradient in a given direction. So basically what the Newton's law tells you, tau yx or tau xy equal to minus mu dv y by dx. Okay, so here you have to remember that the second indices should be same as the direction of velocity. First indices should be same as the direction of the gradient. Okay, dx. Okay, that you have to remember in the Newton's law of viscosity. Then you will not get any confusion. Okay, so first in the second indices in the shear stress term, that is the direction of the velocity. The first indices will be the same as the direction of the gradient. Okay, so what the Newton's law signifies, that here it signifies that the friction force per unit area is equivalent to the resistance to flow friction force per unit area is equivalent to the resistance to flow multiplied by the velocity gradient. Okay, so this is the Newton's law of viscosity. Okay, basically it signifies the friction force per unit area equivalent to resistance to flow multiplied the velocity gradient. Okay, so this law is similar to the, this law is similar to the, okay, so this law, Newton's law of viscosity, is similar to the Hooke's law of elasticity. You have studied the Hooke's law of elasticity in the previous classes. Hooke's law of elasticity in the solid mechanics.
Yes.
So that is the Newton's law of viscosity is similar to the Hooke's law of elasticity. Okay, basically the property of fluid is it will deform. Okay, that's why you have the resistance to flow. And the property of solid is that it will retain its shape. That's why you have the elastic property. The viscous property and elastic property both are the different. In the polymer science, when you study the polymer, you will polymer properties. At that time, you will study the viscoelastic properties. There are some polymers. Most of the polymers are neither solid nor liquid. They are the both. They shows both liquid and solid properties. So you have the viscoelastic properties where the material will deform with time as well as it will also retain its shape. Glass is a viscoelastic material. It will flow again also and it will also retain its shape. Okay, so you have the viscoelastic properties for some complex material. For simple material you have the separate phase. In the solid phase you have the elastic properties. In the liquid phase you have the viscous property. Okay, so this is the Newton's law of viscosity. One important thing in the Newton's law of viscosity, generally Newton's law of viscosity, tau xy equal to minus mu dvy by dx. It is the Newton's law of viscosity. In this case, you can either use the minus sign or plus sign. Okay, you can use both minus or plus sign in the Newton's law of viscosity. Okay, so in above equation. Okay, so when you can use the minus sign and when you can use the, this is basically the a notation method. Okay, so this is similar to the first law of thermodynamics. What is the first law of thermodynamics? Minus u equal to delta u equal to delta q plus delta w. Okay, so either you can use plus w also, you can use minus w also. Okay, so some for in some books work done on the system is positive. In some books work done by the system is positive, and it depends from where you are looking it. Okay, so similarly in the fluid mechanics or in the momentum transport also, you can use minus sign or plus sign both in the Newton's law of viscosity. Okay, so when you use the minus sign, generally minus sign is used in the transport phenomena books. Okay, okay, and positive sign is used in the fluid mechanics book. So when you study the fluid mechanics, you will find people use the positive sign. And in the any fluid mechanics book, you will find Newton's law of viscosity tau xy equal to plus mu dvy by dx. In any transport phenomena book, you will find tau xy equal to minus mu dvy by dx. Okay, so that is only the difference in the notation. Okay, so why this is different? In the in the transport phenomena you have the minus sign and in the fluid mechanics you have the positive sign. So first I will explain you the why in the transport phenomena. Okay, in the transport phenomena generally tau yx or tau xy is represented by the momentum flux. Okay, why momentum flux is nothing, it is a hypothetical quantity. There is nothing like the momentum flux. Okay, flux either you have the mass flux or you have the heat flux. Momentum flux we make a quantity, but it is not a actual quantity. Okay, so basically in transport phenomena, tau xy और shear है ना, that is the shear stress. Is defined as momentum flux. Okay, and in fluid mechanics, tau xy shear stress is defined as friction force. So you understand why it is the friction force, because it is representing, it is actually a friction force. Shear stress is nothing but a friction force, and in actual it is a friction force. Shear stress is defined as friction force. Okay. Now question arises that why we define the tau xy as a momentum flux. So basically, we have, when you study the transport phenomena, you will study the three different types of transport: momentum transport, then the heat transport, and the mass transport. Okay, so here the term arises as a momentum transport. Okay, so when you study the transport phenomena, basically we, you have to make an analogy between the heat transfer and momentum transfer, as well as the mass transfer and the heat transfer. Okay, so in the transport phenomena, you have the momentum transfer, heat transfer, and the mass transfer. So the, in the heat transfer, heat flows from the high temperature to the low temperature. So you have the Fourier's law of heat conductivity, है ना? In the heat transfer, heat flows from the high temperature to low temperature. Okay. Similarly, in the mass transport, the material or the molecules flows from the high concentration to the low concentration, है ना? So in mass transport, molecules molecules flows from high concentration to low concentration. Okay, so when you make the analogy, then you can say in the momentum transport, momentum flows from high shear rate to low shear rate. Okay, so basically, when you write the high shear rate to low shear rate, so whenever you take the difference, है ना, when you define the dvx by dy, so that is the difference. So when, so how you define the derivative? That is the final minus final minus initial values है ना, divide by the v final minus y final minus y initial है ना. This is the way we define the derivative. Okay, so final values is, because it is flowing from the high value to low value, it is flowing from the high value to low value, so the final value will be low. This value has the less magnitude, final value, initial value has the high magnitude. So this is always negative, you know, dvx by dy is always negative. Why it is negative? Because final values is always higher than the initial value. So to overcome this, we use the minus sign. We use the minus sign. Okay, to overcome this, we use the minus sign. Mu is a resistance. It is a resistance. It is a physical quantity. Viscosity is a physical quantity. It has a positive value. It always has a positive value. The viscosities are not never negative. But dvx by dy is a negative quantity because final value, it flows from the higher value to the lower value. Okay, so higher value of dvx by dy is this higher value, final value is higher, and final value is lower, and initial value is higher, and the final minus initial. So here you are flowing from the high shear rate to the low shear rate. So high shear rate is the initial value. This is the initial value. This is the final value. So when you write the final minus initial, you will get the negative sign. Okay, that's why to overcome this, we are using the negative sign. When we study the heat transfer, there also you have the Fourier's law of heat conduction, and in the Fourier's law of heat conduction also we use the negative sign. Okay, and in the mass transport, you have the Fick's law of diffusion. In the Fick's law of diffusion, again you will use the negative sign. Okay, so this is basically the analogy between the all three types of transport phenomena. This is basically the analogy in between the all three types of transport phenomena. That's why we are using the this negative sign in the Newton's law of viscosity. If you are assuming it is a friction force, then friction force again has the negative direction and it is the opposite direction. So you need not to take care of the negative direction in the shear rate. Then you have to use the positive sign in the Newton's law of viscosity. Okay. So you have to just remember that in the transport phenomena, you have to use the negative sign in the Newton's law of viscosity. In the fluid mechanics, you have to use the positive sign. Okay. And why we are using the negative and positive sign? Based on the assumption that we are assuming it is a friction force, or we are assuming it is a flux. And a flux means the property which is flowing. That is the flux. And you have the flux of heat, you have the flux of mass, you have, in this case, we have the flux of momentum. Okay. Any doubt?
No, sir.
No, sir.
Okay. Now, one more thing. Now, the units of the viscosity. What is the unit of the viscosity? So, if you write the units, then it will be mu equal to tau from the Newton's law of viscosity. You can write mu equal to tau divided by dy by dx. Okay, so this is the force per unit area. This is velocity per unit length. Okay, so just substitute the values. So what is the unit of the force? Force is mass multiplied by length multiplied by per unit time. This is the force. What is the unit of the area? That is the L minus 2. And then velocity length per unit time divided by L. This is plus 2. Divided by plus 2. Okay. So this is the dimensions, and we have written the dimensions. Now when you solve this, you will get mass per unit length per unit time. These are the dimensions of the viscosity. So when you write the SI unit, of viscosity, that is kg per meter second. Okay, this is the SI unit of viscosity. The CGS unit of viscosity is that is gram per centimeter second. It is also called the poise. Okay. So, and kg per meter second is also called the Pascal second. This is the another unit of the viscosity, Pascal second and poise. Okay. So one poise equal to, it is represented by P, poise is represented by P. Okay. So 1 poise equal to 0.1 kg per meter second or 0.1 Pascal second. Okay. One more famous unit of the viscosity is the centipoise. So centipoise means Cp. So centipoise is a famous unit of the viscosity. It is represented by Cp. So 1 Cp equal to 0.01 poise, that is equal to 0.001 Pascal second. Okay, so why centipoise is important? Because the water viscosity at 25 degrees Celsius is around 1 centipoise. Okay, so water viscosity at 25 degrees Celsius is nearly equal to 1 centipoise. You know, precisely it is equal to 1.8 centipoise basically. Okay, but that's why centipoise is very important. You know? So the water viscosity is 1 centipoise, not 1.8 centipoise. It is the 1 centipoise. Okay, so the water viscosity at 25 degrees centigrade is equal to the 1 centipoise. That's why centipoise is important, because the most of the simple fluids, general fluids like water, oils, you know, different type of oils, for that the centipoise is the perfect unit, you know, because you have the one or the nearly one viscosities of these units. You know, if you see the gases, for air, viscosity of air is 0.018 centipoise. The viscosity of air is 0.018 centipoise. Okay, and viscosity of the polymeric the melt like PVC melt, and polyvinyl chloride or polyethylene melt. And when you melt the polyethylene, so what is the viscosity of that melt? That is equal to around 10,000 centipoise. So viscosity is viscosity is a quantity which has a very large range. You know? For gases, you have the viscosity 0.018 centipoise for air. है ना. Then you have the water viscosity 1 centipoise. Then you have the polymeric melt which has the viscosity of 10,000 centipoise, है ना. So you have a very long range of the viscosity. And viscosity is a type of property which is changing a lot. Okay. One more thing for Newtonian fluids. This is very important point for Newtonian fluids. Viscosity depends upon only temperature. So viscosity is a function of temperature. Okay, for Newtonian fluids, viscosity depends on temperature only. Okay. So I think this is enough for today's class.
Yes, sir.
Okay, so we will meet on Wednesday. Any doubt?
Okay,
किसी को
sir.
कुछ पूछना है? किसी को कुछ पूछना है?
No, sir.
आप लोग को समझ में आ रहा है?
Yes, sir.